I guess, yep. So we are live now.
Sure.
Hey, folks, welcome back to a new webinar. In this webinar, we'll be talking about AI and computer vision. AI has been in talk for, I guess, last 2 years. We have seen a lot of advancements in AI. Everything or every day, we see a new tool coming up. Offering a different solution in AI. And today we have Mayuresh, who is a CTO at Initialize, and he'll be covering about AI and computer vision. Mayuresh, do you have something to share? If you want to take forward, you can start with this.
Sure. Yeah. So, hello everyone, wherever you are, whether it's good morning, good evening, good afternoon. I'm in East Coast US, so it's early morning for me. Uh, West Coast is still sleeping, I believe, and then I think good evening India. Uh, so yeah, my name is Mayuresh Krishna. I go by MK. I'll talk a little bit about my background, but I wanted to kind of start off by sharing my screen and kind of touching about the subject. And let's see if I can. Let me know if you all can see my screen.
Yep, your screen is visible to me.
So yeah, I wanted to touch upon the AI and computer vision, and specifically now with the advancement of generative AI and ChatGPT, kind of making it mainstream. What is the intersection of computer vision and generative AI, and how has computer vision as a practice within AI has evolved? And if you really look at it, a lot of things which was done in computer vision as well were kind of also kind of led towards the advancements in the generative AI as well. So I'll touch a little bit of history of that, but to tell you all a little bit about myself. I'm Yuresh Krishna. I go by MK to make it easy for everyone to remember me. I'm one of the co-founders of Initialize.ai. I've worked at VMware and Pivotal before, and then a few enterprises before that. You can reach out to me on X or email me on initialize.ai, mk@initialize.ai. We are generally actively hiring. If you are interested in working in, cutting edge field of either computer vision or generative AI, we continuously hire engineers as well as leadership roles in the product side of the world. So, a quick outline of what we are going to go through today. And again, Aisha, if there are any questions, we can start. We can queue up the questions, and towards the end, we'll leave some time for Q and A and have discussion on those as well. So, if anybody has any questions, feel free to put in the chat as I go through the whole discussion. So, from the outline perspective, we'll talk about a little bit of history. So we'll go from SIFT to AlexNet, which are some of the common techniques um, around computer vision and AI. We'll look at some of the history of it. We'll look at CNN, which is one of the which has been one of the primary construct around computer vision, convolutional neural networks. Um, if you think of it, it is like the whole construct of neural networks within AI evolved to be called as deep learning eventually. And then we'll look at transformers. This is where the generative AI comes into play. What transformers did and how transformers has uh, evolved to kind of work on the vision side of the world. And then we'll look at the multimodality things, which is what has been happening in industry of late, and then what is the future from there. So not a lot of topics, but actually all of them have a lot of depth in it. So I'll try to keep it as simple as possible, as well as try to get into the depth of some of the things where it at least intrigues you if you have not actually worked on CV and go you want to kind of start working in that direction. It gives you intrigues you and makes you interested about doing something in it. But I'm not going to get into like the you know 301 levels of what CNN is or what Transformers is. So let's start with a a quick comic. um, shouted from XKCD. I'm sure if all of you might have at some point of life come across some XKCD cartoon. This particular one is on the computer vision problem, and think of it as like we are in 2014. And this is a bird problem, as we call it. And in this cartoon, the kind of user is asking, it takes a photo from the app and should when the user takes a photo from the app, it should check whether they are in a national park. So the engineer, the machine learning engineer says, "Sure, easy. I'll look up I'll look up the GIS and I'll give me a few hours. I'll set this up and make this happen. That where you are in a national park." And then another requirement comes in and check whether the photo is of a bird. And this is where it becomes complicated, and we still don't think of it as in 2014. And the engineer says that I'll need a research team in 5 years to make it happen. Uh, and the construct behind that is like in computer science, it can be hard to explain the difference between easy and virtually impossible, especially in this area of AI and machine learning. And the bird problem is real. So let's uh, and we kind of use this as a grounding exercise to kind of go through the history of computer vision as well. But to bring you to 2024, what we have come through, and this is an example of binoculars from Swarovski Optics. It's not a diamond. It takes high definition photos. You can share things via app, but it also from that binoculars itself classified 9,000 animals. So you can think of like in 2014, we were at a point where it was really difficult to identify uh, animals or a bird, and to a point where you have handheld devices where you can do a lot of these things at the edge. And what a century it has been. And in fact, if you look at it, it's not a century. It has been only a decade. And in that decade, we have advanced quite a bit in essentially everything, whether it's the computer vision side of the world or its generative AI side of the world. So it's been a huge ride. And to kind of set a little bit of context of the history of this, right? During the 1960s and 1980s is where the early computer vision thing happens, right? So if you really think of it, if you look at the overall history of AI, it started in 1950s. Between 60s and 80s, there were some early emergence of computer vision uh, processes of doing things where we were able to do a bit of early pattern recognition and image segmentation, and we kind of got into the construct where you can probably outline through computer vision an image of something and kind of understand what it could look like, right, or what could be. um, in the 90s and 2000s is when a lot of advancement happened, where the machine learning techniques for image classification happened. SIFT and Hog for feature extraction became very prevalent. And then 2010 onwards is where you see the huge progress in CV. And if you really look at it from the perspective of when exactly it happened when AlexNet into the 2012 was able to kind of compete and come out with like great results around the ImageNet competition around image detection, and that was the moment of revolution for deep learning and CV. So, and we'll kind of go into the depth of each of these and see what was happening around then. I won't go into the 60s and 80s. Let's go to the 90s and what SIFT was doing. To start off with, let's take an example of that. I have a bird, a parrot. This is a specific parrot which we are trying to recognize through computer vision. And the old way of computer vision was that we would take the image and we'll kind of identify the key points within the image, and based on that key points, we might do some clustering to understand what portion of that key points belongs to what and what can do, and that led to creating a feature vector. And essentially, this feature vector is we would use to kind of understand what this could be. And like we could, with this feature extraction and feature vector, you would say that okay, this is the these are the different parts of that specific bird around. Like this is the bird's wings. These are the bird uh, beak, and that's what you would do with the construct of extracting key points and then generating your feature vector. And this method is basically called SIFT, which is scale invariant feature transform. Now, this was if you think of it, one of the benefits of this was, and the reason why it was called invariant, because it was able to extract uh, features no matter what kind of angle or light you were in or that object was, and but because of extracting that feature points, we were able to kind of identify that particular point accurately. So. The some of the If you look at challenges of it, right? And this was the old way of doing it, and some of the challenges of SIFT essentially came down to one. It was good with, like, when you have a great resolution of pictures. When you have a bit of distorted or diffused or there was occlusion on the pictures, and like a bird kind of is in front, is sitting on a tree. When you have those kind of scenarios, uh, it doesn't perform well. And SIFT also was initially had patent restrictions, so it was really hard to widely adopt this um, early on. But that's when eventually AlexNet happened, right? And AlexNet breakthrough in the ImageNet competition was the pivotal moment in the computer vision, and how it uh, evolved from there. And you might have all of you might have heard of Ilya, who was one of the early research scientists at OpenAI. He was one of the guy who was working on AlexNet, and uh, Alex, it's behind the name of Alex, where AlexNet into the 2012 kind of made that happen. But like if you look at and again, this was the CNN moment which happened, but CNN has been there for a while. There has been a little bit of history of CNN, that it started off in 1979 with Nicognitron. Then Jan LeCun released LeNet 1 in 1989. Then we had Convolutional Dynamic Systems around 94. LeNet 5 version 5 was launched and came out in 1998. And then in 2012, the whole construct of CNN was evolved and got to a mainstream construct with AlexNet performance. So what I'll do is I'll kind of go a little bit over like what CNN is like, and the construct around CNN, and then we'll kind of get into um, and, and look into the AlexNet's architecture and what it did to evolve the computer vision. So this is just a screen grab from one of the papers, but essentially, uh, to simplify what it is trying to do is, think of it as like you have an input image. It could be, say, 224 by 224 pixels. The convolution essentially is, or you can say it's trying to extract features out of an input image. So you could have essentially, say, a smaller feature set of pixels. So you could go from like, you could do a 4 by 4, or a 3 by 3, or even you can do 6 by 6 sort of pixel window, and it's generally that particular feature window is where it starts off with, and it tries to uh, with that window you're trying to define what it is in that window, right? And then essentially you start with the very beginning of the picture from pixels perspective. So essentially it's going by a block of pixels and trying to identify what's in that pixel, and then it creates a essentially a feature map for that. And so it goes through multiple rounds of that. So it will go, and you would go from, say, starting from left to right. So you go from like one set of pixel feature extraction to go to the next one, and when you move from one to next, how many windows you're moving is called stride. So essentially I could move one stride. What that means is I'm moving from one. So if I'm doing 3 by 3 feature, 3 by 3 filter feature extraction, then I'm going to go from uh, uh, pixel 1 to 3 to 2 to 4, then 3 to 5, from from basically x-axis perspective, and the same goes from y-axis perspective. And then you could do it, that whole construct of kind of building out these features is, or feature building all these filters for feature extraction, goes through the entire set of pixels of your input image, and that filter construct is called convolution. And then from there, um, this requires a lot of resources, and think of it as like if you have a 2224 by 224 image. So if you have a larger image, then you have more pixels to go through, and then filters which you make, uh, you need a lot of resources to kind of go through that. So you go through something called like max pooling, which is downscaling of uh, that filter extract the feature extraction through the filter. So you scale it down further, and you go through multiple of that, convolution and scaling down, convolution and scaling down, where you eventually create a fully connected neural network to understand uh, each filter, and what kind of feature in that filter is there. So at the end of it, it essentially means that looking at a particular picture and its pixels, uh, we would be able to recognize, or the machine would be able to recognize what it contains, what it has, right? And if it finds another image which is uh, equivalent to that, and it matches with the feature extraction, then it would match it with that particular image and say, okay, this is this particular thing. Um, to to kind of illustrate it a little further, and there are several courses, and there are several courses around how what convolutional neural network is, so you can kind of go through that to understand that process of like how that feature extraction happens. Um, to give you a bit of example of like how it could work, and this is very rudimentary way of showing it, but for example, if there's a koala, and if I'm looking at it, how do I recognize it's koala? I'm looking at it, I look at it as a human. I might look at its face, I might look at its features like eyes or nose, its body, and I can deduce that this is a koala. So that's kind of the construct of bringing together multiple perceptions, and then joining it all together in the neural network to understand that this is koala. So I'm going from uh, uh, looking at koala's eyes. Yes, it's koala's eyes. It's koala's nose. Its ears. Koala's hands and legs. I join these in my mind information together, and we got the koala's head and body, and then we join it together to say, okay, this is koala itself. So that's how the construct of neural network works with CVN and in CNN. Essentially, we are doing this feature extraction by these. Say, for example, in this example, 3 by 3 pixels of filters, where we're saying, okay, um, based on our training, we understand that the if it matches within that particular filter, then this is an eye. If it matches within the filter, then this is a nose. This is an ear, and then all that combined matches up in my layers of CNN to be recognized as a head. The hands and legs matches up to be recognized as a body, and then further flattened out to uh, do my classification of that is this koala or not. And so essentially, that's how. And this is a very uh, kind of a rudimentary way of explaining what CNN is and how it is kind of extracting or trying to identify what that image object is. To touch upon what this AlexNet architecture did, and essentially, and if you look at it, this is from the AlexNet paper itself, but ignore the top part of it. Essentially, one of the things AlexNet did is they processed the entire image with two GPUs, and back then GPUs were not that powerful either. So that was one of the things which they were able to do to speed up the process of kind of recognizing an image as well. But essentially, they're doing the same thing. So you have 2 by 20, 24 by 224 image. They took a 11 by 11 pixel uh, uh, filter to do the feature extraction. They did a stride of 4 essentially, so they were moving from left to right, say, for an example, by 4 pixels, and trying to understand or trying to feature extract what is in that particular filter. And then they would do downscaling with max pooling, and then you would do another round of feature extraction. They'll do downscaling again, feature extraction, downscaling again, and then it finally builds the entire dense neural network map for it. So that's how CNN eventually became one of the common ways in vision models uh, to kind of understand what are we looking at from computer vision perspective. So let's look at this bird example, right, and ask AlexNet. So this is one of the spaces in Hugging Face where you can go see if AlexNet can recognize this particular bird or not. So if you submit this image, this particular one came back and said it's a kite. And there are a few other ones which are kind of closer to a bird, but AlexNet to begin with kind of thought that this is a kite, and it's not really a bird. So how do we how so even though AlexNet did quite a bit of advancement, but it was still we still not at that levels of image recognition and computer vision where it can accurately identify things. So what do we need to do to get better now, right? So what can be done? We need to go deeper to kind of understand how, and we need to scale how CNN is done. Essentially, take smaller feature extraction, take smaller filters, go deeper and do feature extraction. And then in the world of CNN, uh, a lot of progress was made, essentially built on top of the construct of AlexNet. And so Google came out with GoogleNet, GooglyNet around 2014. VGG came out in 2014, ResNet in 2015. Uh, excuse me. And then MobileNet came out in 2017. The goal of MobileNet was actually to be able to process these CNN-based image recognition at the edge, at the in the very smaller devices with less resources. So the MobileNet's goal was essentially to go towards like how can we do process this with lesser resources. Then 2019 was EfficientNet, and most recently in 2022 was ComNext as CNN. And to see like which ones are performing better, right? So that's one of the things which industry is looking for, like which method, which model should I use to do this job better. And this is a graph, an example of all the papers um, in around these models in CB, around CNN, and their usage, right? And the number of papers written um, quarterly. And if you see uh, that ResNet has been leading since pretty long, among other, even though AlexNet has been continuously in use up until late 2020, but ResNet has been leading with all the research and the papers getting published in that um, in the area of CNN. So I would assume that you know ResNet would perform better with the bird. So again, I think I have an example of ResNet here. Now this is a bit clip, but I can share the Hugging Face space for ResNet as well, so you can try it yourself. But essentially, you can so ResNet, we gave the same bird, and it came back as hen, 51% hen, 40% kite. So it's not bad. It's a hen is still a bird, right? So it's getting it closer uh, to a bird category as such, but it still couldn't recognize it as a parrot. Like if you think of it, this particular image is a parrot, and say the training in ImageNet data might not have a lot of parrots in there, but still. Um, ResNet and the CNN was still not able to figure out that this is a parrot, but it got closer. It is now recognizing it as one of the categories of hen, one of the categories of bird, like one of the species within the bird category, right? So better, right? And CNNs mostly work from that perspective, right? And if you think of it as there are three different types of things which we try to do with CNNs. One is classification. So for classification purpose, CNNs have kind of evolved to become like one of the de facto ones to do classifications. We can do detection and bounding box almost to a decent accuracy, and then we can even do segmentation where we can extract out the pixels and we can identify like the other pixels of the bird within that particular uh, image. And um, and this has been really helpful. Like if you look at it, and if you try to see what are the different models in this area for different types of tasks. So for classification, you would use VGG or SNet. Connext, WileNet, EfficientNet, all of that would work really well with classification tasks. For detection tasks, you could use faster RCNN, you can use YOLO, SSD, RetinaNet. And then for segmentation, we could use FCN or Mask RCNN, DeepLab or UNet. So there are several models uh, in each of these areas to allow for like different types of tasks we want to do in CNN. Essentially in tasks that we want to do within the computer vision using CNN. And from the domain's perspective, CNNs can be applied essentially in every domain, right? Now, you would see CNNs being used in autonomous vehicles where we're doing the, you autonomous vehicles is trying to figure out what's in front of it, whether it's another car or a pedestrian. It's being used in medical imaging. So in this previous one, UNet is one of the very specific one, which was built for medical imaging. You see the usage in manufacturing and industrial automation, retail, financial services. So pretty much every industry has the usage of CNN, and every domain is it's being used. There's one other thing which I've called out over here is that you can also use CNN for text mining and natural language processing. And this is interesting because, yeah, CNN, like one of the things which you would see if you go take up any course in computer vision and CNN, you'll see there is a image extraction to understand numbers, right? Same way you can do with text. So you can do a little bit of text mining and natural language processing with CNN, but there's a lot which has happened in the natural language processing area in last about, I would say, 6 years, 4 to 6 years, with generative AI and with GPT, right? So let's look at what is the definition of natural language processing. So NLP is the discipline of building machines that can manipulate human language or data that resembles human language in the way that it is written, spoken, and organized. And what was the moment when this whole thing around NLP was kind of the kind of pivotal moment around that was when the transformers happened. And the main, if you look at it, the main paper around transformers was the attention is all you need, which kind of um, uh, kickstarted all of this. Then there was Bird paper which came out. Then there was paper around Roberta, which was around the same thing, and all of that was about like how transformers can be used for natural language processing and text, and all of them talk about like the construct of attention, and attention is what you need. Um, so that's like the, that's the beginning of the construct around generative AI. So say CNN was doing vision, and there was doing it was able to do a little bit of decent NLP and text extraction. From there, when the transformers came into the play in the industry, and I'll uh, kind of take an example of like what attention within the transformer does. If you think of it as like, if I have a word, hi, how are you, uh, each of the word can be broken down in its own token, which is represented by this box, and each box has a query and a key and a value, and essentially the uh, each token is associated with it's kind of the relationship of each token with its adjacent tokens is what is identified, and we kind of come up with a vector called as, based on this uh, essentially calculation, we find out what is the vector of this particular token, right? And that's how the construct of generative AI goes towards the direction of uh, where it could predict what could be the next word or what was the previous word, based on the previous word and its relationship with other words. So when you give hi, how are you to say a chatbot, it will return back I'm good, based on this kind of interdependent understanding of relationship with these different words. How does that kind of affect the CV side of the world, the computer vision side of the world? So in the computer vision side of the world, this evolved to become a vision transformer, and essentially now we are looking at a way where we are trying to understand an image through uh, a transformer lens and a self-intention lens, where we are able to, we're trying to look at how do we uh, what is the relationship between different pixels from each other in that window. And I'm not going to get into the details of like how vision transformer itself works from the construct perspective, but instead of using the convolutional layer of neural network and trying to do filter based feature extraction, vision transformer is using the transformer construct around how do we um, identify an image and what it is doing. So now let's look at this bird, and we can give this to a vision transformer um, model and see how it recognizes it. It is getting closer, right? So lorikeet is a kind of in the family of the parrot, and it recognizes that the probability of this particular image is lorikeet. So it is vision transformer is able to do a little bit better in how we can recognize the image and what it is inside that image, right? And that's where it becomes interesting. And if you look at it, the uh, from like towards the end of 2020 when that paper came out around vision transformer, and since then vision transformer based models have taken over. ResNet is still there, but you'll see a lot more vision models around the vision transformer construct, which are being used in this space with computer vision now. So some of the this again going back to like what are the different tasks which we can do with transformer based models, right? So you have for classification we can use WIT or Dino. For detection we still have YOLOs and Del model, mass Dino models, and then for segmentation you could use SAM or mass former. So there are several different models out there available within the transformers model category to do different tasks. And if I have to really compare, like where you would use CNN versus where you would use vision transformer based models, and the difference between them. So CNN depends on the convolutional layers, and WIT is transformer based, so it's attention based mechanism. Uh, CNN exploits the spatial locality, right? So like what are the different pixels around it in a particular filter window is what it understands to extract uh, the different features within an image, versus vision transformers rely on the self-attention mechanism to understand the relationship of uh, one pixel to the other pixel, essentially within the image. Now, CNNs are computationally more efficient than WIT because in vision transformer, like if you have 1080 by 1920 pixel image, then the number of relationships between the pixels is really high. So you need more processing power to kind of process those images through vision transformers. CNN is effective even with smaller data sets for training, right? So you could give like 5 or 10 images to your model to fine tune with, and it would be effective. Vision transformer requires a larger amount of data sets to kind of train on to perform at the levels which you wanted to perform. So if you look at it, the goal with CNN, and CNN would excel to find, with high precision, a structured image data. For example, if I have a image of say Eiffel Tower, then it can go with high precision and understand the structure of Eiffel Tower. And if you give it any other Eiffel Tower, it would be able to recognize it. The transformer models perform better where you have kind of a holistic image and you want to understand what's happening within the entire image, right? Like you want to get into the complex relationship of like different objects within the image, and that's where the vision transformer excels at. So kind of next came in, and this was kind of driven. This was OpenAI who did this um, work around contrastive language image pre-training or clip around the construct of where they are now. They kind of brought together both the image and the textual data together to understand the matrix of like what are we looking at and what is the definition of it, right? So uh, you have the text encoders coming in, and then you have the image encoders coming in for the image itself, defining like what that image is. That uh, creates from there you were able to create classifications around that all of that image, and we had the label text where now okay, this is an image of a of an object, and that object is a dog. So the combination of the text encoder and an image encoder together now is able to recognize and say and give you a bit more information about what we are looking at in the image. It's not just a dog, but it's able to say that this is a photo of an object, or call this is a photo of a dog. So that was the beginning of further enhancing the construct of the transformer models within vision, to be able to not just detect things but also be able to explain things what it is. So, for an example, uh, in this particular parrot, we gave it a list of labels: parrot, kite, and coconut, and asked what it is, and it was able to identify that this is the parrot, um, and with 100% accuracy that this is a parrot. This is the clip output. There's another equivalent which was siglip, which is also still calling it as a parrot, not 100%, but a parrot. And if you look at it, and in one of the other example of the model around that is Alvit, and I can show you a real example of that as well. But essentially, you have the same construct. It took the text transformer encoder, the vision transformer encoder, uh, got it together to be able to do prediction over objects in an image. And to let's look at this is with image classification example, which we were looking at. So, for example, if I go look at drop this image and infer, and this is just one of the spaces um, within Hugging Face. So it is able to identify that this is an Egyptian cat at 85% rate. Now, similarly, we can go to clip and give it an example and run. It is able to, and we gave it like few labels, which one among this is this. It was able to identify that it's baklava 100%, both clip and siglip output. Uh, when we went to owl and say, for example, let's take an example of this butterfly, it is able to identify which ones are orange butterfly. Or let's do within a human face and give it text queries. Uh, it is able to identify and create bounding boxes around different objects or text queries which we have done. So essentially, with the um with the combination of text encoder and vision encoder, along with the predicting boxes, now with this particular model, all model, you are able to not just identify the object, but are also able to do bounding boxes that particular um, within that particular image using the text queries, right? So you're asking the question that, okay, find me these things within the particular image. So in case of our parrot, uh, when we do a query of is it a parrot or a kite, it is able to find that it is a parrot and give it a bounding box. So that's kind of got into this whole era of multimodal uh, LLMs, right? Where you have not just the uh, image, and that you're just either trying to detect or classify an image, but now you're able to do multimodal aspect to it. Yeah? You can give it a picture or a video or a voice, and you can say, "What can you explain?" And this is what we are seeing in like Chat GPT, right? You're giving different types of input, and multimodal construct is that you have the vision construct here, you have the text construct here, you could have the voice construct here. You could give any of these different types of modes of input, and you could get multimodal output as well, right? You could get an output in text, or you can get an output in another image or a video. You could get an output in audio. So that's where the multimodal LLMs are now in place. So that's where the marriage of CV and generative AI happens, right? Where now you can do the vision things as well as the textual things with a multimodal approach. One of the Quen2 vision language, it is from Alibaba, I think. Yeah. And so essentially you can do it can do pretty much multiple different types of things within that model, right? It can do vision, it can do OCR, it can do document understanding, it can do chat, math and code. So it can do several different things within that uh, vision language model itself. So when we give uh, this bird to Quen vision language, and the question is, please give a detailed description of the image. It can actually go in details and understand and tell you what exactly it is. It says that it depicts Kia, a species of parrot native to New Zealand. The bird is standing on a flat surface. So it's kind of getting into details of explaining the context of the image, not just the object within the image, but it can get into great details of like what kind of bird it is, how it appears, what kind of eyes it has, what kind of road it is sitting on. There's trees in the background. Background is blurred, suggesting a natural setting with greenery. So now this multimodal vision language construct is like the kind of the most advanced direction of where we are with the combination of vision transfer and language, right? Um, Well, that's why I say that vision transformer and large language model combination is uh, has been absolutely amazing in how it is progressing. But where do we go from there, right? What's the future? Uh, and I'm sure all you have what I've seen already seen the diffusion models which are out there, the stable diffusion as well as what Sora is doing at OpenAI. So diffusion models are are they going to be a great feature as well? Then you have diffusion transformer models as well. Um, I don't know if any of you have already played with Sora, but let me see if I can bring up an example of Sora here. If I have one. All right. So let's look at some of the examples of Sora here quickly. And if I say choose this one, and I'm going to try to prompt one live because it takes a little bit of time. Uh, let's see. Generally, they show you the prompt itself. Yeah, so in this one, the prompt was in a pastel bathroom with a rubber ducky, an adorable dragon made entirely of shampoo bubbles. The dragon breathes bubbles. So look at the uh, capability of diffusion models to generate a vivid video, right? And everybody would have already seen um, the some of the um, demos as well as videos around Sora, but all of this is driven by diffusion model within OpenAI. Right. So the future is pretty, uh, I would say, interesting, but also pretty vast. If you look at it, the number of papers published each year, and this is the historical data around active papers out there. Since 2020, there has been an exponential rise of papers being published over there, right? So it almost feels like that 1 hour in our real life is about 7 years in the uh, the area of AI. And I refer to this in quite a different context within AI, but it is true. Like if you are looking at different things to do within AI, it is a very rapidly evolving space. So within CV, what can we do? What can we look at? Like apart from diffusion models, there are several papers, research papers getting published, and like you cannot keep on reading each of them. But I think keep an eye out on different research work which is happening. You might see things being published by OpenAI or other companies around that. Follow those papers. There'll be buzz in the social media which particular algorithm or research work is getting picked up, and there's a trend going on in that. Read about it. So uh, in next, I would say 5 years, there in next 5 to 10 years, there'll be a lot more advancement which will happen in the vision side of the world as well. And then now this whole construct of multimodal, uh, the combination of both vision and natural language processing is advancing this further. So yeah, I mean there's a lot of exciting thing happening in the space. So it's really hard to keep a tab on what all is happening. So I'll pause here. If there are any specific questions, we can kind of get into that. Let me pause
Um,
here.
yeah. uh,
I
thank you
think
for
this is-
sharing all these excellent learnings from your end, Mayuresh. Even I got to learn different things in and around computer vision. What I've did for you is maybe I've accumulated few questions which were
Sure.
dropped in other social media platforms as well. So the first most, I guess you are also able to see. So just for the folks who are very new to this computer vision or AI, if you could maybe just summarize a little on what is actually computer vision, or how is it related, or maybe how has AI changed the let's say past trends of computer vision.
Sure. I mean, think of it as like we when we see things through our eyes, we see in like multiple dimensions, and we see and we perceive image as a human is very different than what a machine sees an image and how it perceives it. So think, almost look at it like, and if you've seen the Matrix movie, you see the bits of zero and ones and like numbers. Essentially, computer vision is when it's looking at a particular um, or any machine when it's looking at any kind of image, how it perceives that image is the kind of the whole construct or the subject of computer vision, where how a machine can perceive an image, then can do things like detecting or understanding what's in that image, going to the lens of even describing the image. So that's the field of computer vision, to understand how a machine perceives an image in front of it. Image, video, a real live feed, all of that can go into this whole subject of computer vision within the artificial intelligence, with the goal that you can do some of these tasks, like you can identify something, identify an object. There are several industry use cases you can apply to it, right? You could do things where as I was saying, in autonomous vehicle, the vehicle is able to understand what is in front of it. In the industry, you could like in general, you could have use cases where you're able to do uh, uh, surveillance and track things. In the industry, you could do quality checks where you have a manufacturing line and something is going through the manufacturing line, and the cameras can look at the parts and try to understand whether the quality of that part is good or not. So all of that, those are the different kinds of use cases which can be applied to computer vision within which is the category within the AI and artificial intelligence.
I guess this totally makes sense. Um, Following on upon your question, or maybe your answer, Mayuresh, you mentioned about autonomous vehicle, right?
Yeah.
Recently, I went through an article where it was mentioned how Ubisoft has introduced photonic computer visions, which maybe gave a breakthrough to a machine perspective thing. So let's say you know, if I ask you about your thoughts on maybe photonic visions, or how can they help in prototyping across various other autonomous things such as vehicles, robotics, ARs and VRs.
Sure. I mean, I haven't read through like what is photonic vision construct yet. Is that like there are so many research which is happening in CV? Uh, uh, you have to keep up with different researches happening. One of the things which in my short amount of work I've done in CV, what I've seen is one of the challenges we still have is that when we look at an image from computer vision perspective, it's still kind of like two dimensional, right? We are looking at a two-dimensional view of a frame and then kind of using those pixels to understand what it is. Um, the I definitely see there could be some advancements in this area where uh, uh, a machine would be able to perceive the image in three dimensions or more dimensions to understand it better. So that's one of the things which I'm also trying to figure out and learn more about and research more about, like how that progress is happening. How do we go beyond just the two-dimensional aspect of understanding an image through a frame?
Um, and I think the most important thing, if we talk about AI, is working with data, or having a good data sets, right?
Yeah.
Uh, you mentioned about let's say models like WITS, like vision transformers. You gave a detailed comparison on CNN and WITS. So
Right.
how do you think like AI-driven models such as vision transformers, they help you address biasness in data sets or data, and how they can help you in maybe let's say filtering your data to be used for a better use case?
Yeah. So there are multiple layers to that, right? One is one is just purely like purely AI construct, like where your output is kind of driven by how good your data is. If your data is not good, your output is not going to be good. Like if you are not able to train with good clean data, you won't be able to achieve the inference and output which you're looking for. But in case of vision model, there are a lot of challenges and considerations which we have to do, and as not just industry, as humans, we have to figure out how, in which direction we are going in with. Right, there are challenges around biases, right? As I said, like what you train your model with is kind of driven by the inherent biases somebody who is kind of collecting and that data and giving that data to the model is having, right? So, for example, if I have a certain bias, that bias might reflect in how I'm training my particular model, and the output is going to be biased as well. And so there needs to be checks and balances around how you are how the human aspect of it, like how we are going about training things, and if how do we address the biases in training data, in how we are addressing biases in by kind of bringing in different diverse views and checks and balances within the construct of training your models. And then the next level of kind of guardrails we need to have is the whole construct of deepfake is very um, it could be destructive for somebody, right? So how do we make sure that we have guardrails around in the computer vision side of the world that there are ways to understand that this is a deep fake, as well as to an extent uh, be able to stop it, right? If it is a harmful content, how do you stop it? uh, One of the things which I'm we are at Initialize actively looking at one of the use cases is to um, identify at the root of any image generation that it's legitimate or not, or it's a real image or not. And what that means is some sort of a way to tag any image I'm generating. If I'm really taking a picture or a video, kind of have some sort of a immutable metadata attached to it, which says that this is a real image. This is a real image taken by me at that particular point of time. Versus so that if there is a deep fake, you could interact with some sort of an API, which could be a blockchain-based API, so that no one organization has control over it, to kind of check and see that is this image real, or is this video real, or is it deep fake, and have to begin with at least have the ability to identify more accurately that that this is a deep fake or not. So there's a lot of ethical consideration as well, right? How do we, as we are progressing on the AI side, how do we kind of manage these challenges, and how do we guardrail against it?
Yep. And I guess I'll take the last question now because we are already above time. So, Mirish, like, what do you think the future holds for the convergence of AI, and how computer vision will help in maybe solving, let's say, global challenges? And when I talk about Gen AI, you also mentioned about deep fake as well. How do we put a wall to these things and work on getting or solving bigger global challenges?
Yeah, I mean, I'm not sure exactly what kind of global challenges we're going to solve, but if you really think of it, any advancements in the industry, right? Whether it was the industrial revolution, and now with now in the era of AI, and like beyond digital revolution, we are in the realm of AI and its evolution. There is good and bad of things, and um, what I would say is that in general, we as humans are able to progress towards the good more than the bad. So AI can pretty much do a lot of things in future. Eventually, I see that it could become the primary uh, task takers and doers in pretty much every field, every industry, in every global scenario. Now, how do we make sure that we are doing more good than bad is what we have to kind of balance out and figure out. But what I'm kind of referring to is historically, we as humans have eventually done more good than bad. It could be argued upon, but I would say that the overall world is a better place than when it was in 1900s or 1800s, or maybe even go back to 1,000 years. So um, I have more faith in the humanity to do the right thing, and and go towards the direction where we are doing more good with these advancements than bad side of the world.
Are we doing good by building AI models? Well, we'll find out in next 5 to 10 years, maybe.
Yeah,
But let's see. Um, Yep. Thank you so much for your time, Mayurish. I guess this was very informative for not only me but for the folks who would be there. Even trying to step into AI industry, and even I guess the folks who would be looking for researchers in AI. I guess this webinar would help them a lot in finding a direction. Do
sure.
you have any closing remarks before we end this?
Uh, so essentially, it's an exciting field. If you, I would say that if you're interested in the area of computer vision, or even in the area of large language models and generative AI, it is pretty exciting right now. So jump into it, learn what's happening. We continuously also hire people in the area of AI. So you can reach out uh, to me as well as other team members within Initialize. But it's interesting field. So I would say that everybody should at least jump into it to understand what's happening here.
Yep. Thank you so much for your time, Ayuresh, and thank you, folks, for joining. We'll see you in the next one. Bye.
All right. Thank you.